All right, well, I will get started here. Let me begin with a word of prayer. Come back to me, computer. All right. Heavenly Father, we thank you for this day again. I thank you for this class and just ask you to bless our work today, Lord. In your name I pray, Lord Jesus. Amen. So I want to talk to you guys about just a little bit more about critical points, vector fields, the study of stability, and also how we can draw pictures, well, not exactly like this, but similar to this by hand for conservative physical systems. So like the basic definition we need to know is just this. So we'll talk about vector fields in the plane here. If you have, F is like F1, F2, then P is a critical point of F if like F1 of P is equal to 0 and F2 of P is equal to 0, or perhaps it could be that F of P is not defined, right? That probably should be accounted for as a critical point as well, I think, in the larger scheme of things. But for the most part, let's be talking about, vector fields where the component functions are defined. Now, the vector field we're looking at up here is, so remember we had the definition of integral curve last time, like if you had dr dt equals to f of r of t, then t maps to r of t is an integral curve, right, of f through, we like to put the point to be like when time is 0. So what we're looking at here in this picture is a whole slew of integral curves for a particular vector field, right? And the vector field that we're looking at is the one that comes default into this aeb019.hosted.uark.edu/pplane.html, which I got as the top result to Googling pplane. So there you go. That comment doesn't have much archival quality, but it's true at the moment. And this has worked for about 5 years, so yay. So like if we were looking for the critical points for the one that's on the board, my vector field, right, is f of xy equal to, so like the dx dt is y minus 1/2 x, if you can interpret the ASCII code, and then sine of x, all right? So, all right, so we either need, excuse me, come on. All right, just a second, I need to feed my computer. It's not like low on batteries, but it's preparing for, a lack of power. There you go. Trade? Yeah. All right.
I was confused.
Yeah, it's cool. So we need sine of x equal to 0 and, y equals to x over 2, right? If I have those two conditions, that gives me a critical point. And in the current context, it's gotten super busy here, but you can see that apparently, you see the 3 critical points here? There's one here, there's one there, and there's one right here. Now, this would be x equals to 0. X equal to 0, y equals to 0, critical point. Where else is sine 0? At what? Minus pi, right? So we got one here, and we got one there. So this is like pi over 2 minus pi over 2. That makes sense? So we can find out where these critical points are for the vector field. Let me do this again. So now it's hard to see without, plotting some solutions, but once you plot some solutions, it kind of gives it away, right? What's going on here? So this is p-plane. It's super useful for visualizing a vector field, even when we actually can't, find the specific formulas for the integral curve, right? We can still visualize the integral curves through this wonderful software. What should happen if I zoom out to like 10? Let me just hit zoom out. Oh, whoa. What are we finding? Interesting, right? Actually, this is very interesting. Let me zoom out more. Oops. Yeah, so there's one at every over x equals to pi. But there's something interesting that's happening, right? In terms of what kind of critical points are we getting, right? So if you look here, the vector field's flowing in that way, and it's flowing in that way. So they're approaching like that, but it's flowing away here and away here. So that's an unstable equilibria. Because if you were to take the solution right there and just give it a nudge, you don't know which way it's going to go, this way or that way, right? These guys, if you take the solution at the at this point, you give it a little nudge, it's just going to spiral back in. So this is a stable spiral. This is also a stable spiral, stable spiral, stable spiral. On the other hand, if you had a spiral that spiraled out, it would be an unstable spiral, right? These are different behaviors that we could have for a vector field. And so we can study the stability of solutions with a picture like this. All right, so I was starting to talk about a system corresponding to a conservative system, right? Like I was starting to talk about, suppose we have the net force is equal to, minus du dx, right? And it's like, okay, so that's m times dv dt, right? And so if I have x1 is equal to x, and if I have x2 is equal to v, then of course I have x1 prime is equal to x2, which is, by the way, v, and I have x2 prime is equal to v prime, which apparently is minus 1 over m du dx. So if we consider the vector field as a function of, let's say, x and v, and that vector field is given by v, comma, minus 1 over m du dx, right? I can study integral curves of this vector field in the xv plane, right? I can study integral curves of that vector field in the xv plane, and in so doing, I can analyze, I can analyze the solution to that equation of motion. So what's the deal with this vector field? If I want a critical point to this thing, what's the condition then? We need, you said v equals to 0, and apparently du dx equals to 0, right? Because we're assuming the mass is non-zero, right? And so what this means is that the critical points of this vector field are in natural correspondence with the critical numbers of the potential energy function. All right, so here's an example. We could have the net force equal to, how about minus kx, right? So that's going to be what? That's going to be like, if I want integral curves to this in the xv plane, I want dx dt equals to v, and I want dv dt equal to what? I think minus kx, right? Minus x? Or is it just x? Oh, you guys, don't let me sell you on this. Is this minus here? Well, yeah, it is there, isn't it? I'm sorry. Give me a second here. Yeah, that's there. That is there. Yes, it is. Oh, okay. All right. So now here's the deal. I don't have software that has X and V in it, right? My software has X and Y. All right. But so I want dx dt equals to y and dy dt equals to minus x, right? So I translate. This is just for the sake of me being lazy and using the existing web software, all right? But if I do that, then we can graph. What do we got here? Dx dt was what, y? And dy dt is what? Minus x, right? Graph phase plane. Let me zoom back into a more reasonable. Minus 2 to 2, 2, 2, graph phase plane. There we go. So this guy, these are, and what are these curves? These curves, I derived it last time. The integral curves to this, right? Turns out that they're just energy level. So like this thing, if I look at mechanical energy for this problem, it's what? It's E equal to basically just, 1/2 mv squared plus 1/2 kx squared, right? That's the potential energy here. In other words, we just get v squared plus x squared equals to, a constant. That's, if you go through the process of finding the integral curve in terms of position and velocity, if we do the integral curve trick, remember dy dx is q over p, solve that by separation of variables, do that for this problem, that's what you get. You get level curves of the energy. And so this circle here, we have to think about what it means. We've got velocity going upward, right? And we've got position going this way. Notice that all of these curves, they're always doing what? Well, excuse me, for above the x-axis, the solutions are always flowing to the what? To the right. Does that make sense? Because dx dt is v, right? V is positive above the x-axis. Of course they have to move to the right. X is increasing. Below the x-axis, dx dt is negative because v is negative. So of course they're flowing to the left down here. That's inescapable for this vector field. Now the one I started class with was much more fangled and interesting, right? But that's not the vector field corresponding to like a conservative force problem here, right? This is a very particular kind of vector field we're studying. It's very boring in some sense because the x component is y, which means it always behaves this way. It flows to the right above the x-axis. It flows to the left below the x-axis. Now, we could have more interesting stuff, like, I don't know, minus, all right. Let's leave the world of conservative forces just for a second here. We go through the same derivation almost, but what happens if the net force has also minus the velocity? That's what? That's like adding a friction term, right? So then the energy will no longer be conserved, right? What should happen to this when I do that? If I throw in not just minus x, but minus x minus y, what happens? See, the energy goes to 0, and of course everything just spirals into the origin. So I can't use energy levels to plot the xv plot for this, not directly anyway. I mean, I can plot the energy, I could make an energy plot without the v here. I could have the, the constant energy levels And then I could add in the friction term and see how that energy is lost, and it toggles to lower and lower energy levels. If I wanted, I could do that. So anyway, getting back to this, let me take the V out again, talk about it for a second here. So what's going on? Like, what's the story? This is simple harmonic motion, right? If you study this going around, like here we have X maximum, right? All the potential energy, it's stretched out as far as it can. What happens? It contracts, right? As it contracts, it pulls back. It gets down to here. It gets down to here. You've got maximum kinetic energy and compressing motion through the equilibrium point. Then it compresses to its maximum compression, at which point your energy is totally potential, right? And then it uncompresses, it stretches back out as it goes through the equilibrium point, maximum velocity, right? In the positive direction. Here was maximum velocity in the negative direction. And then the spring stretches out to its maximum extent, and then it pulls itself back in, right? And this keeps going forever and ever and ever, because that's how spring without friction works. That story is all in this picture. And we could do other weirder stuff, though. Like, what happens if you add, I don't know, a cubic term to your potential? What's that going to do? It's going to do some funky stuff, right? But here is what the so-called phase plane looks like in that system. As you can see now, it still behaves just like a spring, right? It behaves just like a spring close to the origin, right? It's still like a simple harmonic oscillator here. But if you get far enough out, if our potential energy, right? So here my potential energy is 1/2 x squared minus, phooey, fine, 1/4 x to the 4th, right? That's the potential energy. And apparently, it has not 1, not 2, but 3 critical points. One of them stable, 2 of them are unstable. See? Unstable, unstable. Now, I'm not talking about the potential energy at the moment. I'm talking about the corresponding phase plane. How would we graph the potential energy? Well, let me put away the board here for a minute. Because what I wanted to show you today is that we don't need to use the software to do it. We can actually do this through direct hand-to-hand combat with the formula. So let me clean up the board here. So for those of you guys a couple of you came in late, as you may have been aware, Canvas is not working. If you still would like to do the surprise stack mission I just collected from everybody, you're welcome to come up to my office and get a copy. I have a bunch of them copied from Friday when the printer still worked. So you're welcome to come up to my office and get one of those. I got to teach in the next period, so I can't come with you. But they're sitting on my desk. You'll find them. There's a big stack of them. Sort around until you find it. Please don't mess up my stuff. But you'll find it. And then you can give it to me tomorrow. It's fine. But I had threatened to do a surprise attack mission today. Obviously, I'm not going to do that because I couldn't print out the next one. I have typed it up and stuff, but that doesn't help me print it. And the surprise attack mission was just going to be for you guys to do. Basically, it's just for you to do something like I'm about to do right now, which is to graph the phase plane qualitatively by hand. All right? So suppose we want to do these things qualitatively. Now we can be, so your example 3, we want to plot phase plane and potential energy diagram to analyze possible motions if the net force is minus x plus x cubed. All right. So the first order of business is to notice that this is minus du dx. And by the way, as I will typically do in here, we're going to assume that the mass is equal to 1, and I'm not going to fuss with dimensional constants because they just get in the way. All right, so if that's okay with you guys. Well, even if it's not, that's what I'm going to do. So, all right, so first of all, I got to find the potential, right? So how do I do that? So, yeah, minus the integral of minus x plus x cubed dx, all right? So that's 1/2 x squared minus 1/4 x to the 4th. All right? Now, I'm going to assume that u of 0 is equal to 0 for convenience. Obviously, whenever you define a potential energy function, you have infinitely many flavor choices because you can always shift it by a constant unless you're otherwise constrained, right? Like in electrical engineering, many times you're constrained when you're talking about potential because you've set the voltage to be 0 somewhere, so you don't have this freedom. But anyway, there's my potential energy. Next order of business is to find the critical points, which is going to take us, this is kind of silly, because then we're going to look for where du dx, which is, equal to 0. But that's the same as where minus du dx is 0, right? Which was minus x plus x cubed equal to 0, right? I sure hope I'm not doing your homework. Well, if it happened, it happened. But anyway, I didn't give you guys any homework. What am I talking about? What's wrong with me? You practice homework, so yes. I'm thinking of simpler times when I used to actually give homework. But you're saying, it seems like you've given me homework this semester. What are you talking about? What are the surprise attack missions out of class but homework? Fair enough, guilty as charged. All right, so look, this we can solve. That's x times x squared minus 1 equal to 0, also known as x times x plus 1 times x minus 1 equals to 0. Apparently x equals to minus 1, 0, and 1. These are my criticals. Critical numbers, right? Okay, so here's the deal. We make a plot like so. Up here, I'm going to do x, and I'm going to do u. All right. I'm going to attempt to graph. So interesting things happen at minus 1, and at 1, and at 0. Those are the critical numbers. For graphing u, though, it's also helpful to notice what u looks like. What is u? I can factor out a half here, right? And an x squared, and what am I left with? 1 minus x squared over 2. Is that right? Agree? So look, this is 1/2 x squared times, 1 plus x over root 2, 1 minus x over root 2. So like, this is 0 when 0, of course, and also what? Plus or minus root 2. I know it's kind of weird the way I've written it, but that's clear enough, right? So, all right, so that's helpful in graphing because out here at plus or minus root 2, we have x-intercepts of the potential energy. So apparently it bounces at the origin and it crosses at plus or minus root 2, and it's a quartic, right? So what's it look like? It's a quartic that opens up or down? Down, I think, right? So it's got to look something kind of, sort of like this. All right. That should be completely symmetrical if I did my job, because this is an even function, so it's kind of on repeat from plus to minus. So I draw the potential energy up here, and then directly below it, all right, directly below it, I draw my phase plane, my xv plane. All right. And we're going to graph the integral curves to the vector field I talked about over there. In other words, the curves which correspond to the solutions to the equations of motion. Let's see here. If I had been smarter, I'd have brought a ruler. I mean, one with the marks on it, you know, like. This thing rolls. Anyway, you get the idea. This is mine. Parents gave this to me when I was like 17. How dare you? All right. So that's just I wanted to draw the same scale for both. Yeah? Now, like some labels. This is 1, this is minus 1, this is 0, here's root 2, here's minus root 2. All right, great. Now the next order of business, as you saw, is there one possible motion? No, there are many, right? So it depends on the energy level and also your initial position. So like for instance here, right? If that's my energy level, then I kind of go down to here, right there, and that gives me some kind of thing like this. And I'm trying to do the same energy. So let's call this E naught. Now, what are the rules of engagement here? Energy, right, is 1/2 mv squared plus u of x, right? So since 1/2 mv squared is greater than or equal to 0, this means that our energy has to be less than or equal to potential energy. Wait a minute. Other way around. Duh. Because if your total energy is always potential energy plus kinetic, right? So the smallest the energy could be is when it just is potential, which would correspond to places where you're stopping momentarily, right? So like, when is the kinetic energy 0? So like along the x-axis, we have kinetic energy 0. Here, right? V equals to 0. So what's going on is this motion, you can see it better down here. It's going in and then it's repulsed, right? So basically comes in, bounces off. Over here, it's coming in like this and it's going back out. Now, so those turning points, whatever those are, let me call them this point here. for lack of imagination, x1 and x2, right? For energy E naught, that motion, a motion with total energy E naught, is only possible if x is to the right of E2 or to the left of E1. It's impossible, classically speaking, to have motion with energy level E naught between x1 and x2. All right? Now, next up, let me look at a different energy level. I'll look at one that the story is a little bit more interesting, like energy level E1 up here. Now, notice I'm only drawing the line where? I'm only drawing where it's physically possible. All right? If I draw some dotted lines here, where I'm putting the dots, what does that mean? If your total energy was equal to that value there, that corresponds to needing to have negative kinetic energy, which is impossible. So those regions are classically forbidden in terms of the motion. All right? So what that means then, if I can introduce yet some additional labels for the sake of, call this x3, we call this x4, we call this one x5, I'll call this one x6, right? So going down here, here, I should really be using my pools, So, like we get another one of these turnaround deals here like that. Same thing over here like that, right? And then between these two, we get something like that. And the reason for that, again, it's governed by the basic rules, which are total energy has to be this. That's where it's allowed. And also, the more basic thing, just don't ever forget this, is that V is equal to dx dt, right? Which means that the motion has to always flow to the right where you're above the x-axis, and always has to flow to the left when you're below the x-axis. All right? Let's do another energy level. I'll try to do the one that hits right through the, like that, E2. All right? So the deal with that is it passes through these kind of funny points, so it does something like this. Now, if I was doing this exactly correctly, this would be an exact mirror above and below the x-axis here. So any difference between it being a perfect mirror is just my shortcoming in terms of graphing. But that's the energy level E2. It was supposed to be a horizontal line up there. Use your imagination. All right. And then, let's see here, one more, and I'll cease and desist, unless you guys have questions. I guess I'm out of color. I'm back to red again. Hopefully there won't be any room for confusion here. But up here, if I have energy, let's say E3, so notice that for energy E3, the velocity is never zero. The speed is never zero. Since the E3 is always strictly greater than U of x. Right? The total energy, E3, is always larger than my potential energy. Now, if I do this correctly, notice that wherever you hit a critical number for your potential, the trajectory in the phase plane, it has to level out. You have to hit horizontal tangents there, you see, because we're talking about du dx equals to 0, then if du dx equals to 0, what's the nature of the integral curve we're talking about? Well, it's got a tangent, its direction is what? It's v0, right? Which is to say that it's horizontal. and it's either left or right moving. So what I'm trying to say is, as we think about this point right here, wherever it crosses, well, first of all, it's got to be like symmetric from one side to the other, but it should also pass through like horizontally. So it does something like this. And the same for here. So again, up to the limits of my artistry. Now I know it's been a bit, but if you can, if you have a photographic memory and you can think back to what we did on the website before I did this, this is what we saw. There were 3 critical points. The one in the middle was stable, and the ones at plus or minus 1 are unstable, right? It's not an accident, right? The unstable critical points in the phase plane are the ones that correspond to being at the top of a hill in the potential, and the ones that are stable are the ones that are like at the bottom of a hill in the potential. Understand that this is not like, U is not height, but the analogy to height is a useful one. So anyway, any questions? Yeah.
So underneath the green circle, you have arrows going to the left, but if you go to the right, the same lines are going to the right.
Oh no, what have I done? Those are all bogus. Oh goodness gracious, this is why we can't have nice things. Golly, seriously? Ah. Yeah, it should always be right above and left below. I'll forgive my color coding. So all right. So, there's about 20 arrows here. I had 4 of them wrong. So I think that means I get an 80% on my arrows, give or take.
80% passing?
Yeah, sure. I don't know. I have to think, this is an undergraduate course, right? So, I don't know. Graduate courses here are on some sort of wackadoodle 7-point scale. I'm like, oh, horrible. I don't want to think about it. But anyway, I don't teach anything graduate, so it's kind of irrelevant. So this is the phase plane, and if I ask you to plot the phase plane, there's 2 steps. Number 1, plot the potential energy. And then number 2, you can, for given energy levels, create the phase plane plot from that. And this, if you study it, tells you the story of all possible motions. Like things like I said, if you're at energy level E0, it's classically forbidden to have motion between x1 and x2. Now in quantum mechanics, something interesting happens. There's something called quantum mechanical tunneling. And in tunneling, you're allowed to, essentially your wave function can enter regions which are classically forbidden. And so what happens with quantum mechanics is, instead of just being forbidden, there's kind of like a probability that kind of like dies off as you go inside where it's classically forbidden. And so if you're talking about like a spike like this, and your energy is like this, then there's some chance that it gets through and keeps going. This is tunneling. And that's part of the reason that these kind of energy diagrams are important to understand, because like band gap analysis is the heart of the basic understanding of semiconductor physics. You want to understand these energy level diagrams for that, if nothing else. But anyway, let us move on. Next topic. So, see, we would have had just enough time for a surprise attack mission where you did the same thing yourself. Wouldn't that have been fun today? Okay, next time. So what's up next? One of my favorite things, the Laplace transform. And so the first question you might ask is why? Why the Laplace transform? And in a nutshell, the purpose of the Laplace transform is, well, in my view, the purpose of the Laplace transform is simply to allow us to solve problems that have discontinuities in a nice, elegant fashion. It also has significant applications to the theory of signals and systems in terms of the transfer function and all that. So there's more there to talk about. If you want to look it up, there's a professor at MIT who wows his audience by explaining to them in his 20-minute discussion about how it's the continuous limit of something called the finite Z transform or something like this, but that doesn't mean anything to me. It might mean something to you. If it does, I'm so sorry, but it's on YouTube. But for me, it's just a tool to solve discontinuous problems. All right? So here's the definition. The Laplace transform of f of t is a function of s, and it's equal to the integral from 0 to infinity of e to the minus st times f of t dt. To which you should say, what? I mean, that's a weird definition, but here it is. And so example, I'm starting the examples over. This is example 1 for Laplace transforms. I'm starting at 1. Like, what's the Laplace transform of the constant function 1? All right, so what's the integral of e to the minus st with respect to t? Search your heart and find it to contain e to the minus st divided by minus s. You had to evaluate that thing from 0 to infinity. Don't tell the other math professors I wrote this, right? That's a notation for a particular limit. Yeah? And so what's this equal to? Well, e to the minus s times infinity over minus s plus e to the 0 over s, right? And that's equal to 1 over s provided what? What condition do we need to know that e to the minus s times infinity is 0? And of course we intend that in a limiting sense, truth be told, but if s was negative, would this work? We'd have like e to the positive very large number. Does that go to 0? No. So we must need the condition that s, the so-called frequency, is greater than 0. So electrical engineers will say s is the frequency domain, whereas t is the time domain, whatever that means. But for us, it's just going to be s and t. So there you go. The Laplace transform of 1 is just 1 over s. So far, so good. All right. Example 2, Laplace transform of e to the at. Let me do ct, actually. E to the ct. So there we got integral from 0 to infinity. E to the minus st times e to the ct dt, also known as the integral from 0 to infinity of e to the minus parentheses s minus c times t dt. So we have e to the minus s minus c times t divided by minus parentheses s minus c evaluated from 0 to infinity. Again, so we're going to get, I'll leave the 1 over s minus c out front. And we'll have like e to the minus s minus c times infinity minus 1. So in order for that to converge, what condition do we need on s as it relates to c? It has to be greater than c. Very good. So the Laplace transform of e to the ct of s is equal to 1 over s minus c, provided s is greater than c. All right. So now we got 2 Laplace transforms. All right, great. Check this out. So if we were to say the Laplace transform of f is equal to big F is a nice notation. that we like to use in here. Then df ds is equal to, the integral from 0 to infinity of the partial derivative with respect to s of e to the minus st times f of t. When I bring the total derivative with respect to s inside the integral, it becomes a partial derivative because the expression inside the integral is a function of both s and t, and as such, this is a partial derivative. What happens there? So that's what? Integral from 0 to infinity. That's minus t, right? E to the minus st. F of t dt. Agree? Okay, so we can pull that. So apparently, the integral from 0 to infinity of e to the minus st, right? Times t, f of t dt is equal to minus df ds. But what is this? It's the Laplace transform of t times f of t. Multiplication by t becomes differentiation by s with a minus. That's kind of wild, right? And okay, so what's the Laplace transform of t then? Let's apply this theorem here. What's the Laplace transform of t? It's minus dds of the Laplace transform of 1, right? Which is minus dds of, well, we just worked it out. Laplace transform of 1 was 1 over s, right? So we've got 1 over s squared. Next up, what's the Laplace transform of t squared? Well, that's minus dds of the Laplace transform of t, right? By the same token, we can do it a second time. And so that's minus dds of 1 over s squared, which, by the way, is 2 over s cubed. You see where this is going? I mean, we can keep doing this.
N over s to the n plus 1.
Yeah, Laplace transform t to the n of s is going to work out to, looks like n factorial divided by s to the n plus 1. And there you go. That's the Laplace transform of t to the n. All right, so far, we've got Laplace transform of 1, Laplace transform of the exponential, and now we have the Laplace transform of t to the power n. Next time, I will derive for you guys Laplace transform of sine and cosine, and then we'll start looking at how we can solve differential equations with this, all right? So there are problems we could not solve before that we'll be able to solve with this method. It really is something new. But anyway, I shut up.